One situation where our model applies fairly obviously is a situation where we've invested a certain amount of money and it grows at a certain rate of interest. The differential equation becomes the derivative of the principal amount A of t, or the amount in the account at time t, with respect to t is the rate of interest times the amount in the account. So A of t is the amount in the account at time t, and R is the interest rate. If that's given as a percentage, then it's R divided by 100 we're using. If we invest $0 in an account, paying R times 100% interest per annum, and the interest is compounded continuously second by second, the amount in the account after t years is given by A of t equals A0 times e to the RT. So for example, if I invest $1,000 for 5 years at an interest rate of 4%, where the interest is compounded continuously, then this follows our exponential growth model. And if I want to know how much will be in my account at the end of 5 years, I have A0 is 1,000, R is 4 divided by 100, which is 0.04, and because this interest is compounded continuously, we have the amount after t years is A0 e to the 0.04 times t, which when I fill in the details is 1000 e to the 0.04 t. So when t is 5 years, the amount after 5 years is 1000 e to the 0.04 times 5, which is approximately $1,221.40. How long do I have to wait before there will be $2,000 in the account? Well, in this case, we must solve for t. We know the value of A0, we know the value of R, and we know the value of A of t that we want in the account at time t. The unknown is the t. So we must solve for t in the equation A of t, which is 2,000, equals A0, which is 1,000, times e to the RT, which is e to the 0.04 t. Now the only unknown in that equation is t, and we can make our life simpler by dividing both sides by 1,000, and we must solve for t in the equation 2 equals e to the 0.04 t. Taking the natural logarithm of both sides, we get the natural log of 2 is 0.04 t, and t is the natural log of 2 divided by 0.04. That's approximately 17.33 years, so we must wait approximately 17 years before our investment doubles. Now, sometimes interest is not compounded continuously, and if I invest an initial amount A0 in an account with an interest rate of R by 100% per annum, the amount in the bank account after t years will of course depend on the number of times the interest is compounded per year. So if the interest is compounded once a year, then the initial amount is A0. After 1 year, I have that initial amount plus R times A0 in the account, or A0 times 1 plus R. At the beginning of the second year, my initial amount is now A0 times 1 plus R, and at the end of the second year, the interest has been applied to that amount. So therefore, the amount in the account at the end of the second year is equal to the amount at the beginning of the year times 1 plus R, which is A0 times 1 plus R times 1 plus R, which is A0 times 1 plus R squared. And after t minus 1 years, I have A0 times 1 plus R to the t minus 1 in the account, and then in the tth year, the interest is applied to that initial amount, And at the end of the tth year, I have a naught times 1 plus r to the t minus 1 times 1 minus r in the account. So at the end of t years, I have a naught times 1 plus r to the t, where t has an integer value here. Now, suppose that the interest is compounded every 6 months, so twice a year. So at the end of 6 months, the teller sits down, figures out how much was in the account at the beginning of that 6-month period, and adds r over 2, the interest rate divided by 2, times that amount to the amount in the account. So for example, if n is 2, that is the number of times the interest rate is compounded, and I invest a naught, then at the end of 6 months, I will have a naught plus r over 2 times a naught dollars in the account. In the next 6 months, that interest is applied to the a naught times 1 plus r over 2 dollars in my account. If that's the initial amount, the amount at the end of that next 6 months is that amount times 1 plus r over 2. So at the end of the first year, I have a naught times 1 plus r over 2 squared dollars in the account. So each year, the amount in the account gets multiplied by 1 plus r over 2 squared. So at the end of t years, I have a naught times 1 plus r over 2 squared to the power of t dollars in my account. And of course, if the interest is applied monthly, then at the end of 1 month, I multiply a naught by 1 plus r over 12 to get the amount in the account at the end of 1 month. That happens 12 times a year, so at the end of 1 year, I have a naught times 1 plus r over 12 to the power of $12 in my account. And every year, the initial amount gets multiplied by 1 plus r over 12 to the 12, so at the end of t years, I have a naught times 1 plus r over 12 to the 12t dollars in the account. So for any given n, if I start with the principle of a naught, at the end of n years, I have a naught times 1 plus r over n to the nt dollars in my account, and you can see that as n tends to infinity, we're tending towards the situation where the interest is compounded continuously. At the end of t years, I will have the limit as n goes to infinity of a naught times 1 plus r over n to the nt dollars in the account. But of course we know that that limit is e to the rt. So it agrees with our assessment for continuous compounding of the interest that we had before. So let's see, if I borrow $50,000 at a 10% interest rate for 5 years, and the interest is compounded quarterly, how much will I owe after 5 years? Well, we have the amount after t years is going to be the initial amount times 1 plus r over n to the nt. And we have to figure out what r is and what n is in our formula. So a naught is 50,000. The interest is being compounded quarterly, so n is 4, and the interest rate is 10%, so the r is equal to 10 over 100, which is 0.1, and this is the amount I will owe after t years. After 5 years, I plug in t equals 5, I'm going to owe approximately $81,930.82.